Hello everyone, welcome to the HSPF training by DSI. In this video, we will review an HSPF model that was created by BASINS and focus on the things that we should quickly improve before we go into the calibration process. So let's look at this UCI file that was created earlier. So now these land uses are based on the initial DBF file that we provided and that I showed you in the HSPF340 video. So I will not go into that. Now these parameterization, 101 is supposedly water or in wetlands, and similarly 201 is water wetlands and 301 is water wetlands. Now BASINS provided a default parameter of to all of these operations, and it gave a value of 0.16 inches per hour to all of these uh, operations. Now that value is bogus, and it actually, if you look at it, then there is a starter UCI file in the default BASINS installation. It provides values based on that UCI file. And my suggestion is to edit that starter UCI file, and or after your BASINS model, HSPF model is created, you edit this infiltration value based on BASINS technical note 6. So let's look at the starter UCI file. Okay, so the starter UCI file is located in C drive BASINS 45 models pin 31 pin starter. So that's, if you have a default installation, this is where you will find the starter UCI file. And let's open that also. So it has some parameter values initially set up, and when BASINS creates an HSPF model, it gives the values based on this starter UCI file. And it says 0.16 for all of them, all of the land uses, forest, urban, that it has some default uh, land uses. Either you should edit the starter UCI before you make any model, or you should edit this UCI file, because this, if you start with 0.16, your model will be wrong. Additionally, HSPF BASINS provides the same slope and length value for all the land uses in one segment. So water, wetland, forest, all of them have same LSER and same SSR. Now that is definitely wrong, and BASINS does not have capability to calculate slope for each operation. What I generally do is I calculate the slope of each purlin and each purlin separately in a different GIS software, and that I use to fill here. Also, these LGSN values are do not make sense, so you will have to change it. Then other thing is that it groups all of these parameters. So pivot palm 3, pivot palm 4 are all grouped. That means all the land uses have same deep traction loss, base ETP, upper zone nominal loss, and all of these values are same. If you have a watershed model, these values should change based on the land use and based on where they are located in the watershed. So it's always a good idea to go ahead and vary these values based on the uh, land use. So for example, agriculture might have different UZSN value than forest, and you should consult BASINS technical note for that. Then MON interception, the monthly interception table that it's provided. This table is same for all the land users and has the same value for each month. My suggestion is to make sure that this change according to the season, and then you provide different interception storage capacity based on the land use. Similarly, it's not so important for yeah, impervious land, but you may want to look at the SLSR and ELSA parameters, and other parameters may not be that important. Then we look at F tables. So BASINS makes default F table based on the drainage area. Most of the times they work fine because in a watershed model, the the peak flow rate are the things that are generally affected by the type of F table. However, when the flow rate is low, then the F tables can also affect the flow for longer period of time. For example, here the area is 21.91 acre when the volume is zero. It means that when the stream starts getting drier and drier and drier, the area exposed to the atmosphere for potential evapotranspiration does not change significantly. And that means the evaporation becomes, um, there's a lot of evaporation happening on a very small amount of water, and that can cause some instability in your model where you may have you may suddenly see a very high concentration of some nutrients because all the water got evaporated, or you will see the problem in the low flow simulation because you will see the low flow simulation going down quicker because all of that water that is available for very low flow, that all of that gets evaporated very quickly. So you may have to go and adjust this area and change it significantly. So these are some of the quirks of the model that is provided by BASINS. Again, this is for a generic F table with certain drainage area. Now you may have watersheds that have pipes that have other designs, and you may want to change your F table based on that. So that is a very project specific question. So some of these basic things that you should do before you even get to the next step of model calibration. One another thing that I suggest to look at is look at the potential evapotranspiration data. And so in this case, we use the potential evapotranspiration from NLDAS. And I have not looked at it for this model yet. We can actually quickly look at it. File, manage data, analysis, list, no, constituent PEBT, attributes, add. We have the sum annual. So BASINS will quickly calculate sum annual of all of these data. Okay, so it's about 52 inches, 46 to 52 inches for potential evapotranspiration for this watershed in Minnesota. I think that is too high. So you have to consult with the local watershed managers, or you can look at the atlas to figure out what should be the free water surface evaporation of this area. And then you may have to use multipliers in the ext sources block. So here PEBT, you may have to use multipliers to reduce the potential evapotranspiration that is applied to the model. So these are some of the things that are my suggestion that you should do before you go into the process of investing your time and resources in modeling and getting the observed data and comparing it with the observed data. So that's it for now. This finishes the HSPF 300 course, and where we learned how to make HSPF model from BASINS for one model segment, two model segment. We also reviewed the UCI file that it created. If you have any questions about it, please let me know, and I'll Go ahead and add an additional video to clarify if there are more questions. Other than that, we'll move from here, we'll move to HSPF 400, where we'll work on the calibration, hydrologic calibration of an HSPF model. See you in the next course. Thank you.